Hi everyone, my name is Krish and welcome to OpenSteam. Today we are going to cover a much more technical paper, zero-shot denoising via neural compression. If you're in the ML field, you're familiar with zero-shot, and this paper discusses a technique to have a noisy picture purified through neural compression. Basically, we give a neural network a noisy picture, and this neural network has never been trained on this kind of case scenario before. This is the first time it's experiencing something like this. And we have an algorithm that does compression on it, and through that compression of the image, we'll also be able to clarify it and reduce the noise from it. This has application in medical imagery, it has application in astronomical imagery, and anything that has a lot of noise naturally in the pictures itself. So in this case, we have discussed two common noise models, AWGN and Poisson noise. AWGN is a much more normal or simpler noise to handle because it's identically distributed along all of the pixels in a picture. On the other hand, Poisson noise is something which is dependent on the signal itself. The signal in this case, you can consider it as a pixel or something which is emitting light in this case in the image itself. So in this case, we can tell that if the brightness is very less, we can expect that the noise will be more because you will be able to specifically highlight the point where noise can be there because of the low brightness, if you get what I mean. So these are the type of models that we're going to be considering. Now, the core idea in the compression-based model is that structured or non-noise signals are very uniform in nature. And if you consider it as an example, if you're walking down a road and you have your earphones in and you're listening to a favorite song, that song is very structural. It has reasons behind every melody that it plays. On the other hand, the noise on the road, the traffic and any sort of hecklers, anything, that is very unstructured. It happens randomly. You're able to easily differentiate between what is noise and what is not noise. This happens the same way in images as well. Something which is meant to be there is much more structural than something which is not meant to be there. And this is why we're going to use compression in this case. So we're going to come back to this architecture, but we're going to first cover the step-by-step pipeline so that we are going to understand what exactly is going on. And of course, I'm going to cover the paper itself soon enough, but just so we understand this first. So firstly, we have to have a single noisy image, just a single input that we're going to use on a neural network that has never been trained on something like this. Because these kind of denoising algorithms usually take huge amounts of data and huge amounts of self-supervised learning, which is very compute heavy. So this entire process is very compute intensive because of the large amount of data sets needed and because of the current ways as well. But this method, because it is proposing something which is zero shot, the compute is very less and you don't need any sort of data set as well. We're just working with a single noisy image that it experiences for the first time. The algorithm itself is the innovation. So firstly, because we have an image, we'll put them into patches, and those patches will be overlapping. That we can have, of course, you understand what overlapping is, but that is how we want to break the entire image. So once we have done that, then we are going to use an untrained neural compression network, optimize the encoder, decoder, and using distortion and rate loss, and tune the lambda iteratively. These are all terms at the moment, but we'll get to them eventually and understand what exactly all of them meant in some sense. So once we have all done that, we're going to get to the denoising phase where we use the inference. We feed the same patches through the trained network, and this time the compression removes the high entropy noise. After being done all of that, we just finally aggregate everything. We're going to come to this aggregation later, which is very important as a step because it improves the quality a lot. Right. So Once we have covered all of this, now let's try to understand what exactly is going on. If you go to the paper, we have many examples of what exactly worked before and what exactly this paper is trying to do next. It's a very math heavy paper as well, but we don't need to get much into that. We're just gonna understand exactly what's going on. So, as I said, structural data in an image is very much easy to identify compared to something which has noise. If we have a compression network or a compression algorithm that is planning to compress an image, we are just going to make that entire process cost effective or cost conscious. That is why we have included the term of entropy in this case. Noisy data will be high entropy. It will have lots of variances in it. Whereas something which is very clear and structured will have less entropy. And if we have made this entire system cost effective and we consider this currency to be bits, suppose we have to compress an image, the system itself has limited bits to expense. The system will automatically choose the pixels which are not noisy because it wants to save that currency, and it will automatically start to forget about, or not forget, but start to ignore the noisy parts. For example, if you're talking to someone and they're talking in a very muffled voice, like over a call, and they're trying to tell you something important, like something about an exam or something about a health emergency, you'll try to pick up only the most important stuff. If we consider the example of the health emergency, we'll try to figure out something which is along the lines of ICU or along the lines of what happened. And in the terms of an examination, we'll try to figure out what exactly is going to come in the exam. So we will automatically ignore the noisy parts, we'll automatically ignore what is not important. This is exactly how this compression network is working and is trained. And because this entire system is just trained on a single image, in fact, the overlapping patches of the images, it doesn't really matter what exactly the dataset is. We can work with what is just given. Another important term in this paper is the lambda. The lambda is the fidelity versus compressibility factor. It defines the entropy limit. As I said, this currency, this entropy that is maximum allowed, this is defined by lambda. And we are able to tune this lambda according to what we need. Right. So as I was saying, lambda is fidelity and compressibility, the factor between it. Fidelity and compressibility basically just mean how much data was compressed and how much essence and how much value of the original picture that we are left with, so that we don't lose most of the features because of the compression itself. Now, so far I think you have understood the flow itself. We basically have a simple compression network which is just working with an algorithm that has specific budget to how much it can work, and it will automatically by nature give preference to the pixels or the signals which are structured and non-noise, and we'll just simply ignore the noisy signals. So once we have covered and understood this entire process, we are going to come towards the entire process as a whole now. So encoder, the latent representation, the quantization, and then the decoder. Now we're going to just next cover up what exactly is lambda again and how do we choose lambda correctly according to the case scenario. Every type of image that we have and the noise that we have with it, it will have a noise variance, and how much can the noise essentially differ by. And this is how we choose the lambda. We will know exactly how to figure out when an image and the entire process is overfitting or over smoothing in this case. Smoothing in this regard is just losing out all of the features that we are representing. Now let's cover up the pipeline yet again. We have the first step, the second step, and the third step. By step 3, we have carried out the compression task and automatically used it to figure out what exactly works and what exactly does not work in terms of noise, of course. Remember, in the first step, we chose overlapping patches. Well, according to the study being conducted during the making of this research paper, they found out that the most amount of reference or the most amount of features that you get out of a pixel is when that pixel itself is in the center of a patch. Now, because we have overlapping pixels, we can only not just depend on those kind of patches, we also have to depend on the surrounding patches as well for additional information. Because who knows what pixel actually depicts in terms of another pixel, the relationship between them. So that's why we are representing it using overlapping patches. Once we have done that, the final step is aggregation. This aggregation reconstructs everything into the into the image grid, and the holy grail in this case are the overlapping patches, as I've told. Now, the aggregation itself is something that we have to understand as a final step in the entire process that actually brings everything about and puts a tiny bow on it. In this case, as I've said, the center patch often gives the best kind of estimate. And this is basically the entire paper in the sense of the theory itself. The experiments run are something that makes us understand that this kind of zero-shot denoising system works as a state-of-the-art model, and we are able to reduce the amount of data sets required and reduce the amount of compute required by a lot. And that is about it for this paper, zero-shot denoising via neural compression. This video was much more on the shorter side because I wanted to cover the theory basically of what exactly is going on in terms of the pipeline itself. If you want, let me just show you all of the equations ones as well, because that is of course the main crux. These are the set of reconstructions, and in this case, this is the case for the AWGN, the Gaussian noise in this case, and we also have a factor for the Poisson noise as well. So as you can see, the difference is a bit about the factor that we include according to the type of loss we are calculating. For reference, we have this. Yep, these are the formulas for the same. And when we're done with that, we have the compressor based denoiser, of course, and in this case encoder and decoder networks. So theta1 are the weights of the encoder and theta2 are the weights of the decoder. The encoder decoder itself are standard ones, nothing different in that. What we are only playing with is the entire algorithm, and this is the lambda hyperparameter, as I said, and it actually of course depends on how much we are playing with the noise itself. Yeah, according to the experiments, the most basic output that we had was its state of the art. And of course, this paper, all of the credit goes to these three authors, and I was just discussing it, of course. So thank you for watching. Hopefully I got your mind all steaming, and that's about it.